last lecture we have proved that if we have a collection say x alpha, tau alpha, where alpha belongs to some index set j, this is a collection of Hausdorff topological spaces, then this implies then this is given, then the product space phi x alpha, alpha belongs to j with respect to the product topology is also a Hausdorff space. So, that is for that how we prove was take f g belongs to the product space, then with f not equal to g, then for at least one alpha belongs to j, then this will imply f of say some alpha naught not equal to g at alpha naught for some alpha naught belongs to j. Now, go to the corresponding coordinate space x alpha naught. Here f alpha naught, f at alpha naught, that is what normally we call it x alpha naught, this is some y alpha naught, both x alpha naught, y alpha naught belongs to x alpha naught, and this space is Hausdorff, hence we will get some u alpha naught, a open set in x alpha naught containing x alpha naught, that is f at alpha naught, and another open set say v alpha naught containing y alpha naught, such that, and second first this and u alpha naught intersection v alpha naught is empty. See, then now take a new open set u, we can either you call it phi a alpha, alpha belongs to j, where a alpha equal to the whole space x alpha when alpha not equal to alpha naught, and a alpha naught is u alpha naught. Similarly, we take the set V by say b suffix alpha, alpha belongs to j, where b alpha equal to the whole space x alpha when alpha not equal to alpha naught, and b alpha naught is v alpha naught. Then this u v open sets in our product space containing f u open set containing f V open set containing V open set containing G and U intersection V is nothing but pi, U is pi A alpha intersection pi B suffix alpha, then this is same as pi of A alpha intersection B alpha, which is empty because I mean this pi of correct A alpha intersection B alpha, alpha belongs to J, which is empty, since when alpha equal to alpha naught, the corresponding A alpha naught intersection B alpha naught is same as U alpha naught intersection V alpha naught, which is empty. So, hence the product space is Hausdorff. Even in this case, even if you replace product space by box topology, that product topology by box topology, the result is true. So, then we have seen that I mean more generally some symbol exercise. You have say x1 tau 1 a given topological space and x2 tau 2 another topological space, and you have subsets say A1 subset of x1, A2 subset of x2, then this implies A1 cross A2, this is subset of the product space x1 cross x2. Now, if it so we can take closure of this set with respect to the product topology, this one way, and we can take the closure of A1 in x1 tau 1. So, that is A1 closure. Similarly, closure of A2 in x2 with respect to tau 2 A2 closure. Now, they are subsets of x, this Cartesian product is subset of x1 cross x2. So, we can prove that these two sets are same. So, that is just take an element say order pair, here take an element order pair say x1 comma x2 belongs to our A1 cross A2 whole closure. So, A1 cross A2 whole closure. Always does see what we aim to prove is now to prove is the order pair x1 x2 belongs to A1 closure cross A2 closure. Now, that means x1 belongs to A1 closure and x2 belongs to A2 closure. This implies, that is, this implies x1 belongs to A1 closure, say yeah, x1 belongs to A1 closure, and I mean this is to, that is we have to prove that x1 belongs to A1 closure and x2 belongs to A2 closure. This is to prove, that is to prove x1 is in A1 closure, x2 is in A2 closure. So, what will, so take an open set say U1, in our topological space x1 containing x1, U1 open and it contains x1. Similarly, take a open set say U2 open set containing x2, that is open set in our topological space x2. So, this we have taken. Then consider this U1 cross U2. Now, this is a basic open set containing order pair x1 x2. Then we have taken order pair x1 x2 belongs to closure of A1 cross A2. So, then that will imply this U1 cross U2 a basic open set containing order pair x1 comma x2, that will imply this, and order pair x1 x2 belongs to, it is given is this belongs to A1 cross A2 closure. So, hence this intersection A1 cross A2 is non-empty. So, this is non-empty will imply we will have an element say some order pair y1 y2, see which is in U1 cross U2 and A1 cross A2, that means y1 belongs to U1 and also it will be in A1, that means U1 intersection A1 will be non-empty. Similarly, y2 is in U2 intersection A2. So, that means if we start with a open set U1 containing x1, U2 containing x2, then we can prove that U1 intersection A1 non-empty, U2 intersection A2 is non-empty, that will imply x1 belongs to A1 closure and x2 belongs to A2 closure. Is all right? Yeah. So, hence
x1 x2 belongs to A1 cross A2 cross,
yeah.
Then x1 comma x2 belongs to A1 cross A2 the whole closure.
Yeah, let us just recall what is some question. So, we started with order pair x1 x2 belongs to A1 cross A2 closure. So, we wanted to prove that that is in A1 closure cross A2 closure. So, we wanted to prove x1 belongs to A1 closure, that means what, take any open set U1 containing x1, then we should prove that U1 intersection A1 is non-empty, that is we will have to get an element y1 which is in U1 as well as A1. So, that is what we have got a order pair y, because this set is non-empty. So, that will imply there exists order pair y1 comma y2 which is in the intersection. This will imply order pair y1 y2 is in the first set, mean y1 is in U1, it is in A1 cross A2, that means y1 is in A1. So, that will imply y1 is in the intersection, correct. So, hence this intersection is non-empty. How we got this is using the fact that this order pair x1 comma x2 is in the closure of A1 cross A2. Similarly, we proved that y2 is in both U2 as well as A2. So, hence this U2 intersection, similarly we proved that this y2 belongs to U2 intersection A2 is non-empty. So, when this is true for every open set U1 containing y1, U1 intersection A1 is non-empty. So, that imply x1 is in A1 closer, similarly that x2 is in A2 closer. So, that is what we wanted to prove. So, exactly the similar way we want to next we have to prove that A1 closer cross A2 closer is a subset of A1 cross A2 the whole closer. Now, take an that means take an element say order pair x1 comma x2 say in the left hand side, that means x1 is in A1 closer, x2 is in A2 closer. Always start with to prove is order pair x1 x2 belongs to A1 cross A2 closer. So, this is to prove. So, what is enough to prove that for each basic open set containing order pair x1 comma x2, that basic open set should intersect A1 cross A2. So, we will consider only a, it is enough to consider a basic open set, it is of the type U1 cross U2, basic open set in our product space containing order pair x1 x2 belongs to here. That means now U1 is an open set containing x1, but x1 is in, so we have taken x1 belongs to A1 closer, that will imply this U1 intersection A1, see that is x1 belongs to A1 closer, A1 closer, U1 open set in x1 containing x1 implies U1 intersection A1 is non-empty. Similarly, we have x2 belongs to A2 closer, here U2 is an open set containing x2, then using that we can prove that U2 intersection A2 is non-empty. So, then take some y1 in this U1 intersection A1, y2 is in U2 intersection A2, then prove that that is the common element for A1 cross A2 and U1 cross U2. So, that will prove the other part, I mean that is this will give the reverse inclusion. So, the in fact one can prove that if we have a collection of topological spaces and A alpha subset of x alpha, alpha belongs to J, then this implies phi A alpha, alpha belongs to J. So, using the same idea we can prove that this is also equal to phi A alpha closer alpha belongs to J. See, main thing we should note here is what is a basic open set in the product space means phi U alpha, alpha belongs to J, where each U alpha equal to the whole space x alpha except finitely many alpha 1, alpha 2, alpha n. So, this concept is more important, that is essentially to know how a basic open set looks like that. And now we will introduce the concept called connected topological spaces, and there again we will come across the product space. I mean will the main result there is how to prove the product of connected space is connected. So, let us start with what is called connected, that means when we say a topological space is a connected topological space, connected topological space. In fact, it is negation is easy to visualize, that is connected in when you say a so given a topological space x tau, what do you mean by this is not connected, or x can be separated by means of open set, that is a topological space, this we write for a topological space x tau is said to be a disconnected, that means not connected, said to be a disconnected topological space if and only if this set, if and only if, can be written as union of two open set A, which is non-empty, and another open set say capital B, which is also non-empty. See, now the union of these two set is whatever x. So, x equal to here x equal to union of A and B. So, it is like from you are in the other side of B in A, from A in some sense you cannot reach B. So, keeping this motivation in mind, we define a topological space x tau is said to be a disconnected topological space if and only if there exists non-empty, so underline here non-empty open sets A comma B in the whole space in X, satisfying the condition, namely first they are disjoint, A there is no common point between A and B, A intersection B is empty, second, but X equal to union of A and B. If such a pair exists, then we say that the topological space x tau is disconnected, or let us say not connected. So, then what is a connected topological space mean? There cannot exist a pair of non-empty open set having these properties. Then we say that negation of this statement. If it is not disconnected means we say that it is a connected topological space. Mean what are the trivial example? In fact, when we say that x disconnected mean we are able to write x as A union B, this is non-empty open set in X, capital B non-empty open in X. So, hence this will imply the set capital B, one is the complement of another. B equal to A complement and A equal to B complement. So, we have both A open mean A complement is closed. So, that will imply capital B is closed. Similarly, B open imply A equal to B complement imply A is also closed. So, in other words, what we have is there exists a non-empty, there exists a non-empty set or so in fact. So, what we will remark is a topological space X tau is disconnected if and only if there exists a subset capital A of X such that A non-empty, not only A is non-empty, complement also non-empty, that is means A not equal to the whole space. A is non-empty, A not equal to X. So, there exists a subset A of X such that one this and second A is both open and closed. That means A is open, A complement is our the set B. So, B is nothing but A complement. So, enough to find a set which is non-empty not equal to X, which is both open and closed, then such a topological space is disconnected. So, in effect, if we start with a take X is here, see let us what will happen if we start with this X any set, let us say tau discrete topological space. See what is the what will happen, discrete topological space, hence tau, this implies tau is nothing but power set of X, that is every set is an open set, every set is open means complement D is also open. But can what is the suppose take a set A, let us suppose that X is non-empty, then we can take a subset which is non-empty. But what will happen if suppose let us say A contain only a single element, then A is non-empty should imply in this particular case A X is a singleton set, it is a singleton containing one element say small a, then A contain only singleton A. So, then what will happen to, then this will imply A complement is the empty set. So, what we want is we want a set A non-empty and not equal to X. So, here A is non-empty, but it contain only singleton. So, this will become the whole space. So, we are not able to get in this case a set, a subset A of X, say that A is non-empty, A not equal to X. That means even with discrete topological space, if our X is singleton or even X is empty, then we will not able to find such a set A non-empty not equal to X, and that set is both open and closed. So, we cannot find such a set means that topological space is connected. So, to want to give an example, so we will assume that X is any set containing at least 2 elements. The cardinality means at least 2 elements. I mean, in other words, the cardinality of the set is, if it is finite, at least 2, or it may be an infinite set. So, in that meaning, and tau discrete topological space. Now, we can get a non-empty set because A contain at least 2 element. Now, even if we take A is a singleton, then A complement will be again not equal to non-empty, not equal to X. So, which is both open and closed. Then such a topological space is disconnected. X any set containing at least 2 element tau discrete topological space, then this discrete topological space is disconnected. In fact, easy to give examples of discrete, I mean like discrete topological space, you can give many. Suppose you in fact other simple example, take X is any set, define X any set, suitably we will assume that, I mean what condition we should put on A on X, and A subset of X, say that A complement also, I mean subset, and such a way that A complement also non-empty not equal to X. So, A also non-empty not equal to X. So, then you consider even tau, we have empty set, the whole space A, capital A, which is non-empty not equal to X, that is in tau, the complement is also in tau. Then this is also a topology on X. I mean such example may not be that interesting. So, this with respect to this topology X will be disconnected. So, now we will give an example of a topological space which is connected. Mean again we take, it is take X, in fact we have seen that X will, let us assume that it is an infinite set. Geometrically it will not be that clear. Take X any infinite set, our tau f co-finite, that means the complement of every non-empty open set is finite, co-finite topology on capital X. Then this topological space, so we are giving an example of connected topological space. So, then this X infinite set together with co-finite topology is a connected topological space. So, that means what, we will not able to get a subset which is non-empty not equal to X, and that set A is both open and closed. So, let us see what will happen, suppose proved by contradiction, because we are familiar with how the open sets are proved by contradiction. That means start with any, suppose there exists a subset A, subset of X, say that A A complement, yeah, or that is either way, that is subset A such that A is both open and closed, meaning is A non-empty not equal to x and A belongs to tau f, where A is open and the complement A complement also belongs to tau f. See now here it is trivial, A is non-empty means the complement of that set should be finite. So, A is open, it is a non-empty open set, that is important. A is non-empty, A open, that means A belongs to tau f, imply A complement is finite. It is a finite subset of the given space X. Similarly, A complement, see A not equal to X, that means A complement is cannot be empty. So, A complement, if it is empty mean again the complement A equal to X, but A not equal to X. So, A complement non-empty, A complement also because A is both open and closed mean A complement belongs to tau f, imply complement of this set A complement of A complement, that is A is finite. So, that is we have A complement is finite and A is finite, that will imply this union. So, this now A complement or finite sets mean finite subsets of capital X. This imply X equal to A union, the complement is with respect to X is also a finite set, is also a finite set, that imply X is a finite set, but our assumption is X is an infinite set. So, if you assume that there is a subset non-empty not equal to X which is both open and closed, then we will get a contradiction, hence such a set cannot exist. So, that imply our topological space X infinite set tau f cofinite topology, then the cofinite topological space is in fact connected. So, hence we have proved that X tau f is connected when X is when cardinality of X is not finite, when X is an infinite set. In fact, what will happen if it is finite set? Then the topology is discrete. So, that case it will be disconnected provided it is contain at least 2 elements. So, now in fact we will let us prove that in geometrically we feel that what are the connected sets in R, not only in R or even later we will see in R2. We will prove that intervals are the connected sets in R, and in fact they are the only connected sets in R. So, intervals are connected sets. In fact, first let us prove intervals in R connected set. So, let us recall first what is an interval. Of course, in what is an interval in R or the set of real numbers. So, we are using the particular order, the standard usual order relation. So, suppose say capital X on interval, I mean again So, we can assume that X contain at least 2 elements, either empty set or singleton, that will become connected. So, our interest is as cardinality of X is greater than or equal to 2. So, X is interval in R. So, if and only if you take any, if and only if it satisfies the following condition, x y belongs to whichever we are calling is interval x, and x y belongs to x. Say take a x is in capital X, another y is in capital X. Interval mean all the points between x and y should be also in X. So, and suppose Z is any element or Z or okay, Z is any element between x and y, x y belongs to x, x less than Z less than y implies Z is also in the set X. So, then we say that it is a connected, sorry, it is an interval. So, now let us assume that, so X is an interval containing at least 2 elements, 2 real numbers, at least 2 real numbers, then let us prove that it is a connected set. So, in fact, it is a nice theorem. Geometrically what we feel is in no gap between members of the set X, then it is connected. So, X interval in R imply X is connected. Again this will approach by contradiction, I mean either direct also will be similar. So, let us suppose that, let us suppose that there exist open sets, there exists non-empty, but we are using the definition non-empty open sets capital A comma B in our space X. So, what is that is, note that what is the topology, this is tau topology, usual topology on R imply tau restricted to X is set of all u intersection X such that u is open in R. The open set, you take an open set in R, restrict that open set in X, that is an arbitrary open set in X. So, this we are familiar. So, let us suppose that there exists non-empty open sets A B in X such that it is satisfying the condition that they are disjoint. So, 1 A intersection B is empty, A and B are disjoint open sets. 2 we take but the union A union B equal to the whole space X. So, now you see geometrically we have A is non-empty. So, we have, let us suppose that there exists non-empty open set A B. So, take an element, prove, take an element X is in A, and let us say, so we can Z belongs to B, I mean that in between element we will call it some y. So, we have, so it does not matter, we do not know which is x is less than, at least it cannot be same because they are disjoint. So, either x is less than z or z is less than x, we can without loss of generality, let us assume that. So, assume that, so x is strictly less than z. So, if we call it z less than x, that you can call it x and this is other. So, x is in A, x which is in A, z which is in B. So, now see x, this set closed interval x is in capital X, that means it will contain all the points in between also. So, if we take any point between x and z, because it is an interval, that will belongs to capital X. Capital X is nothing but A union B. So, that element is either in A or in B. So, keeping this in mind, what we are going to do is collect all those elements from the set A. See, for example, A is non-empty because x is there. Next, collect this element, those y in A, say that, I mean this is essentially what we are going to take is, take this interval x comma z. This is the standard notation, all the elements, set of all real numbers between x and z, including x and z. So, we are considering this interval. Now, take that intersection with A. See, here x is here and x is in A, x is here. So, hence this set is non-empty. Then just you want to see how far we can go. After some stage, see, at least z is not here. So, obviously z is here because z is in this first set, but z is not in A. So, z is not here. So, we cannot reach. So, we will just go to the stage, beyond that stage all the elements are from B. So, we will that to reach that we take the what is called least upper bound of the set x closed interval x comma z. Now, take the this closed interval x comma z intersection A. This is a because bounded subset of R. So, we call it say supremum of this set, supremum of this set, that means this is same as supremum of set of all say A, say that A belongs to closed interval x comma z intersection A. In fact, it is a nice close, I mean the supremum will exist. So, let us see, first of all, yeah, that is our LUB axiom. So, if we the LUB axiom says that if it is a bounded set, then it has an upper bound. So, all the elements in this set will be less than or equal to z. It has an upper bound, then it will have the least upper bound or supremum exists. So, that supremum let us say, so let us fix that as y. This y is now fixed, that is supremum. That y is, let us call this is our some supremum. So, now all the elements between this, if we take any element, take x, this is z, this is y, take any neighborhood of y, properties of supremum. So, we can, that means for every epsilon greater than 0, y minus epsilon, y plus epsilon, this we can restrict to even x. So, this will contain elements from this even intersection with x. So, this will contain elements from left side. So, that means this will be a what is called limit point. See, this y is a limit point of the set A. So, that means y belongs to A closer. Similarly, so this will imply, this will see y belongs to A closer, but closer with respect to x, and similarly we will prove that if we take the, it contain points from right side. So, this y will be in the intersection also. So, that will give a contradiction. So, using this we can prove that there cannot exist a separation. That means we go till the end y, that y the supremum will be in both A as well as in B. So, and that will give a contradiction. So, we arrived at this contradiction if you assume that they have a separation. So, let us complete this in the next lecture in the remaining part. Thank you.